And welcome to Crash Course Sir David R. Cox. Today we're going to talk about his important statistics-related accomplishments. First, let's talk about logistic regression. We've all heard of linear regression. It's how we estimate linear relationships between two quantitative variables. But what if we want to find a relationship where one of the variables is categorical? David Cox wanted to help answer this question in order to be able to predict whether mechanical failures would occur and to make other categorical predictions. Let's go to the thought bubble. To estimate whether an AP Stats student will pass their AP test based on how many hours they spent studying the week before. First, what result do we want to get from the regression? In a linear regression, our output is a specific possible value. For example, a person who's 5'10" might have a predicted weight of 150 pounds. But if we just predict that a person who studied for 8 hours would probably pass, that's not very informative. Instead, we want to estimate the probability of passing. So maybe someone who studied for 8 hours would have a 90% probability of passing. We might try to use a linear model to estimate this. But when we try this, we run into a problem. We've just predicted that someone who doesn't study at all would have a negative probability of passing. We need to make sure to keep the outputs between 0 and 1. We'll use a logistic function, which looks something like this. Notice that the graph of the equation always stays between 0 and 1, so it's always a valid probability. That expression on the left is called the log odds. It's the probability of passing divided by the probability of failing, and the logarithm of that ratio is taken. Now, we can just use a regression in a similar way like we do for linear regression to get a good fit for the model. Next, let's talk about the Cox process. It's a type of point process, which is essentially a distribution, except instead of random numbers, it describes random points on the plane. Instead of just one random point, it describes a distribution of several points at a time. A Cox process is a more advanced version of a Poisson process that accounts for variability in the parameters. Just like how the t-distribution is based on the normal distribution, but accounts for variability in the standard deviation, the Cox process is based on the Poisson process, but accounts for variability in the parameters of it. It's used in finances to model prices involving credit risk, as well as in biology to model action potentials of neurons. Talk about the proportional hazards model. The proportional hazards model estimates the time until some effect occurs. It might be used to estimate lifespan. Its key assumption is that an increase of some amount in an independent variable creates a fixed multiplier to the risk. For example, each cigarette smoked in a day might double the chances of dying of lung cancer. It's made of two parts. One part is the baseline hazard function, which gives the explanatory variable as a function of time, for example, number of cigarettes smoked in each day. The other part is the parameters, which describe how much the cigarettes affect the risk of death. Cox's work in modeling this allows statisticians to estimate the parameters, how much cigarettes affect one's risk of dying, without knowing anything about the baseline hazard, how many cigarettes were smoked in each day. Not only is this useful for medical research, as it can be used to estimate the relative dangers of various activities, habits, and treatments, but it can also be used in engineering and a wide range of other fields. Thanks for watching. Make sure to like and subscribe in the comments below, and leave a subscription in the comment box underneath. Thank you!